0.04. 0.04. -20. -20. Maximum speed. Oh, wait. Wait, I could have just, one half.
Yeah, you can just use this because this is a
Oh, whoops.
deducing
Yeah,
function.
this is too much, too much.
Okay.
1/2. 500. 4 squared.
Mm.
That equals 4,000. And then this equals 1/2 mv squared.
Mm.
0.025. 4,000 over 0.025. It's 400 meters per second. 400
400 meter.
second. Wait. Oh,
That's a little too fast, right? You realized 400 meter per second is
wait.
very fast.
4,000 equals 1/2 mv squared. Wait.
Are you using 4 meter? It's 4 centimeter.
Oh, right. The 0 point. Okay, that makes sense. Oh, so then this would be 10.
Yeah.
Oh, so it'd be 20 meters per second.
What do you mean, 1 second? Oh, okay. 1/2, they simplify is basically 0.05 times v squared equals to k. K is 500 times 0.04 squared. So this is 500 times 0.0016. So it's a 500, let's say I time it 100 in here, I time this. So it's 5 times 16 divided by 5. Wait, I think it's v squared is 16, which v is 4.
V is 4?
Hmm.
Wait, it's 10. 10 equals, wait, 1/2 times 0.05 times 10. Wait, yeah, how did I get, that doesn't make sense.
I think
Wait,
the left,
0.5?
yeah, I think it's the,
I think it's 0, wait, I got 0.5 when I did it again. Wait, no, what? Wait, 500 times v squared. Okay, wait,
I think it's
Zero.
this calculation. Can you
One
do
half.
20 like 250 times 0.0016?
That's 0.4.
Oh yeah, that makes more sense. 0.4 and then divided by 0. What's the other side? 0.025. Is it 16?
Yeah. Wait, 0.04. 0.4 divided by 0.0. Yeah, it's 16.
Okay, then that is. Yeah, then it's 4. Does that make sense?
Yeah.
Calculation, right? First is the
Mhm.
union conversion and then it's calculation. Oh. Yeah, this is the thing about physics. We like to do estimation to check. It's pretty easy to make mistake. So anyway, so this is energy transformation, right? From elastic energy, actually from the work that we do. And then we translate into elastic energy. And elastic energy translated into kinetic energy. Right? We normally use like a U as potential energy, or US, which means spring. Or you can say US, the elastic energy. And then let's take a look at this graph. So we can say this at this point. Yeah, at this point, which means the amplitude, when amplitude happens, this is the maximum, right? Velocity is 0 and what is the K? Oh, doesn't really matter. So US in here is 0, and then you transform all into velocity or kinetic energy, right? Does that make sense?
Mhm.
So if we talk about acceleration, where do you think the acceleration is the largest? You know, in these 3 positions.
1.
Yeah, 1 has the largest acceleration, which is in that direction. This one also have large acceleration in that direction, right? So you can, when you move from here to here, the acceleration is getting less and less till you reach into the, well, equilibrium position. Next one, 3. 3.
Okay. Amplitude. Amplitude is 0, 0.8. 1/2. 500. 500. 0.8. What do they mean the total energy of the oscillator?
Well, the total energy is just when you pull, this is either you pull or you compress. If you press, then you can have the energy all in elastic, right?
Mm-hmm.
But later you decrease your elastic energy and making into kinetic energy, right?
Oh. So the total energy for this is
You can add these two together, or because of this, well, conservation, you can just find the original, the starting elastic energy, which is the total energy, right?
yeah.
Total energy is okay because since it's the conservation of energy, so it's just the original elastic energy would be fine. Of course, you can also use kinetic energy and add with the elastic energy later, but the original one is easier, right? Just find the original, which is what you just did, right?
Yeah. So it's 1.6.
Yeah. Let's say J, and then the speed of the block.
When it's 4 centimeters. 500. One time 0.04 squared equals 1 2 b squared. Um. Okay.
Wait, I have a question. You
Mhm.
want in this equation, you think all the energy originally transform into kinetic energy,
Oh no.
right?
So then, so then we
Those are
need to use
different.
X, right?
Yeah, we have some extra energy other than kinetic energy at that moment, I think.
So we have to subtract from the 1.6.
Yeah. From the total, you subtract that elastic energy, then what's left is going to be transformed into kinetic
This is
energy.
1/2 500 0.04 squared.
Yeah. And that's also kinetic energy.
Uh,
Mhm.
4 squared. 250. 1.2. 1.2.
Yeah, V squared is 1.1.
1.1.
So now we have both. At this moment, we have elastic energy and the kinetic energy at the same time, right? Don't forget add those two together. So this is making sense, right? Also, conservation of energy works here too. Example 4.
Hmm. 1/2. Wait, 1/2. 500 a squared equals 1/2. Wait, then b squared. So a equals 0.25.
Yep. So 25 centimeters. It's 25 centimeters is also not that long, and it's making sense, I guess. You learn wave, so you heard the period and frequency before, right?
Yeah.
Period is just for one cycle, how long, how many seconds, right? Does that make sense?
Yeah.
And frequency basically, well, just 1/t, right?
Yeah.
Like for 1 second, how many cycles you make? So this is their relationship between frequency and time period. Example 5.
T equals 1/f. Time equals 1/. Wait, 1/. Wait, f is frequency in this one? This is frequency.
Oh, you mean this?
Yeah, wait, is that frequency equals 1/time?
Yeah. What do you mean?
Okay.
1/time. When you say time, you mean period, right?
Oh, so period is t.
Yeah, period is t. This is period. Period. Not just
Okay.
any time.
Oh yeah, okay.
For
I
one
see.
cycle.
I see. Look, awesome.
One cycle.
Motion is position max. Period of frequency. 0.25/1. Wait, so 0.25 equals t. F equals 4.
They say from position of maximum.
Oh, so
Spring
that's
stretch.
half of it. So that's half
Yeah.
of it. 0.5. So that means frequency is 2.
Yep. And to the unit is what? Hertz. Remember?
Oh, hertz, yeah.
And the period unit is basically seconds, right? But this is certain time. 1 second. Yeah, don't forget whether they give you period or half the period. Yeah. It depends, I guess. 6.
6. A student observing an oscillating clock counts from 1 minute. Frequency 45.5/60, which equals 0.753. And so the period is Wait,
783.
wait. Yeah, 7583.
Yeah.
And then sub period is 1.32 seconds.
Yep.
Right.
Yeah, that's good. So some people say this 45.5 cycle of like in 1 minute, isn't that, well, frequency already? It is frequency. It's a one kind of frequency, but the frequency that we like normally, is how many cycles you do in 1 second. It depends, especially the one that we recently learned. So in the future, they say this is the frequency. Yeah, it's also true. But the frequency that we like to use in here, I mean, recently AP1, it's gonna be 1 second. How many seconds? So that's why I divided by 6. And also when we have the, when you have Benji in here, up and down, the period is certain. So what is the period relate to? Or frequency relate to? Can you imagine if a person is heavier? Does it take longer for he to complete 1 cycle?
Yeah.
So mass is related, right?
Yeah.
And also it depends on the spring constant of that spring, right? Or that string. Does that make sense? So the spring constant is also involved. Probably more spring constant, which means if the K is higher, you can measure T is probably shorter, right?
Right? Yeah.
So which means they are inversely proportional, probably. So we probably have M for the denominator and K as the denominator. Does that make sense? Actually, what they try before, it's something like this. But actually, the data doesn't really work in here. So then they try something else. They get all the more and more data. What they find is this. Is the square root of that. Which means if you divide it, sometimes they have this in experiment. Sometimes we just if you find T, you find M over K. It's not a constant that you have, which means it's not proportional. But if you find this square root of M over K, let's say if we have a lot of data, okay, have a lot of M, have a lot of K, have a lot of T, and it turns out 3 of them doesn't really have any pattern. But later when you find square root of M and K, they have. Does that make sense? So what is like a T over square root of M over K? So there must be something. T square root of M over K. It actually turned out as 2 pi. In the future, we will prove that why simple harmonic motion is related to the 2 pi, or it's basically like circular motion. In the future, we will do, for example, this. I just show, because proving is not a part of what the test wants, so we kind of skip it. We do have a way to prove it. For example, you imagine this one is moving from here. It's a circular motion to here. At the same time, this oscillator from here into here, into here, into here. I mean, this is 1 cycle. And this is also 1 cycle. And you can imagine that this and I have a shadow in here. So every time, see this correspond to the. So that's why it somehow connect with the circle. And so t over square root of m over k is 2 pi. So eventually we have a equation t equals to 2 pi square root of m over k. These two connect together can totally prove that. So this is the period, and also it's proved by the data table. So if this is the case, then I have my frequency is also kind of popular. So which is one over this entire thing, right? 1, 2 pi and k over m. Both works. Maybe on the same experiment. Let's do 7.
Frequency equals 1 over square root of 300 over 2. 50. $150. Wait. 1 over 2 pi. So you can go 19.24, and then
Wait, this one is a 3. This part is a 300, right?
Yeah. Whoops. That's not clear. Yeah, it's 300.
300 divided by 2 is 150. 150. Basically, square root of 150 times the 1 over 6.28.
I had to like round it. Wait. 6 point.
I think a 19 is a little too big. Probably.
Wait, I can try.
So 100 is a 10. It's a
Oh,
little
wait,
bit more than 10.
I did this wrong. Wait, hold up. Wait, I can check. That's over 2. Wait, 2 over. Okay, wait, 2 300. The S is on 0. 0.513. Oh, wait. Wait, that means this is 1.949?
Oh, yeah, 1.9 is probably.
95.
Yeah.
No.
Yeah, 1. And the unit is what? 1.9.
Hertz?
Yeah. No. And so you just take, actually you can just use 1 over 1.9, right? Seconds. It's probably 0.1 and 0.5. And is it making sense? 1.9 for a block. Probably making sense. And 0.5 for a period. Yeah, I guess. Example 8.
Example 8. Block is attached to experience at the accelerated motion, which frequency is measured. Okay, so we're seeing, let's say, let's say K is 1, then frequency equal 1/2 pi root 1/m, and then compare that to F. F was 1/2 pi 1/1/4, so that's 4/m. Wait, 1/m times, wait, 1/1/4 m. We come up with 1/1/4 m. Wait, 1/1/4 wait. That equals, wait, 1/1/4 m, isn't that
4/m, right?
yeah, that's what I wrote.
You are consider K equals to 1, right?
Yeah,
Okay, it's easier because it's easier, right?
yeah.
Because it's the same thing, we can pretend it's 1.
Well, if we're comparing, oh, we're comparing their frequency. So then that's 1/√m times, okay, so this would be 1/2 pi root m. And so this one would be 2 over root. So 2/2 pi. So the frequency doubles.
Yeah. So if the block becomes 1/4 and the frequency doubles. Yeah. It's probably making sense now. And let's say 9.
Example 9. The student performs an experiment with string blocks. They put an oscillation that's 3 centimeters long. Wait. Amplitude of oscillation is 3 centimeters. Amplitude of oscillation is 6 centimeters. Period frequency and natural period plot between the two trials. M is 1, K is 1. So the first trial is 1/2 times 1 times amplitude times 3 squared. That's 9/2 for the first one. Period frequency and maximum speed between these two trials. 1/2 pi times the square root of M over K. Wait, is it K over M for frequency?
Oh, if you get confused, I try to, well, because for me, period is easier. So, and because it seems pretty easier to get it from the observing. So this is T. But then the other way is frequency.
Okay, let's do T then. Okay. Mass is 1. So T equals 2 pi. So F equals 1/2 to 1/2 pi. And then a frequency and period, they're the same for both. So
Yeah. Because M and K doesn't change, right?
yeah, and wait, this is the total energy for the first one. 1/2 1 V squared. 2 cancel out, V equals 3 in the first one. And for the second one, 1/2 1 and 6 squared equals 18. And 18 equals 1/2 mv squared. 2, 3, 6 equals v squared. V equals 6. So the velocity doubles.
Yeah.
And everything else stays the same.
Yeah. That's why just well, same thing in this case, velocity is just proportionate to amplitude, right? U double and I double, right? That makes sense?
Mm-hmm.
You can also deduce something kind of like this: 1/2 mv squared equals to 1/2 k a squared, right? See, and this 1/2 and 1/2 simplify, and m, it basically is m over k equals to m over k equals to a squared over v squared, right?
Mm-hmm.
So m over k is the same, and so that's what u double I double. Because m over k is a constant, it doesn't change. So basically a over v is a constant number. So that's why U double, I double. Telling me?
Mm-hmm.
Yeah. Deduce all the ways there. So 10.
Each of the effective spring constant. This is a force constant on single spring that produces. It's a pair of. Can you scroll down?
Just 4 there, one.
Oh, wait. Okay. Determine the effective spring constant. This is a force constant, a single spring that produces effective force. Can't you just add them together? Wouldn't it just be K1 plus K2?
Yeah. So you can imagine that this one is pulling him, this one is pulling him, right?
Yeah.
Yeah, so that's why it's basically negative K1x plus negative K2x, right? And divided by x, which is 1 over K1 plus K2 negative. If this is F. Yeah, K1 plus K2. Good. Second one.
Oh, whoops. This one's going this way, and this one's going this way. Wouldn't it be K1 minus K2?
Yeah, that's the instinct. But for example, if I push it in here, you can see that this one is giving a polling, right? And this one is giving a. You push this one, you also give this, right? To the left, which means you probably can't really subtract, right?
So you need to find the total.
So the F total would still negative Kx, K1x plus negative K2x.
Yeah.
Yeah. So eventually the K total is still, I guess it's still K1 plus K2, right? Like before.
Yeah. Oh, I see. Okay.
So B is a little bit against our instinct. And C.
What's the dot?
The dot is just you connect one spring and another spring. This is the connecting point.
Is this just also K1 plus K2? Oh wait, this one would be.
We normally should just make it X happening. What you want is F total divided by the X, right? And eventually it's the K total.
Yeah.
What's your F total?
So this one's pulling this one here. This one's also pulling that one here. If you do negative X, push and then that would push everything together. And so F total equals F total equals negative K1x negative K1x would be minus K2x.
Yeah, that's what some. Yeah. Sorry, someone also wrote that, but we still have to prove it. The process, one of the key here is because I can consider, although it's two spring, but I can consider, but they're connected. I can consider they are like a system, so they are like one spring too.
Yeah.
When I say one spring, which means the force is the same. which means what you feel the force in here also is the force in here, right? So if it's the same force, which means the same force is actually F total. So it's just F for K1, you have F, you have K1, right? For K2, you have F, you have K2, right? And this indicates something about X1, which means the displacement for K1 spring, which is X1 is negative F over K1, right? And then same thing happened here. X2 is negative F over K2, right? So X1 plus X2 is going to be my X, the total displacement. Does that mean? So which is negative F over K1 plus negative F over K2 is going to be my X, right? Which, well, because eventually I want to find F over X is going to be my K, right? K total, right? This is right, K then. So I get an F in here. So it's negative 1 over K, 1 over K1 minus 1 over K2, right? So this is X. I might want to get a negative sign out. So it's a negative F over X equals to 1 over K1 plus 1 over K2. Is that making sense? So eventually, if I find a common denominator, and then I flip, which is K1 times K2 over K1 plus K2. Is that making sense? So this would be the total, or you can say use their word is the K effect, right? K total. So eventually it's K1 times K2 over K1 plus K2, which is a little strange though. You see that this is similar as the one that we do circuit. Have you?
Circuit? Like electrical ones?
Yeah.
Yeah.
This is series, right? But if I do parallel, like that, do you remember?
Oh, I don't think I learned this.
Oh, then okay, we will learn it in the future. There's something there. So anyway, the K effect would be K1 times K2 over K1 plus K2. So that's C, okay? How about D?
This K equals K. This one would be 2K.
Yeah.
This one also 2K.
Yeah.
And if this one, if they're both the same, so it would just be K?
So the C is this, right? I'm gonna substitute it because the K, so it's K times K over K plus K, right? K squared over 2K, which is K over 2, right? Yeah, so eventually for D is K over, so all the other A, B, I mean, for C is, not D. It's like, well, 2K, and K over 2, right? Yeah, have you played that in the gym? They like a certain, if you have this kind and this kind, and 3 of them. Make sense? If you make more, which means it's more difficult to pull, right? Does that make sense? Because there is a gym equipment in the, well, at least I saw it before when I was little, those kind. So I get more of this, so it'll be more difficult for me to pull it, right? For exercise. First you try 1 and 2 and 3. So which means you don't really see something like you don't really get one spring, another spring, another spring, another spring. I see people do 4, the one that I did, like this, just to practice their muscles. But no one do it like this, right? If you got 4 of them, you can imagine it's getting smaller, right?
Mm-hmm.
The strength is getting smaller. Next one. Let's do 11 and then summarize.
One goes mass is attached to the end of a vertical spring. Force constant K equals 300 meters. After the block comes to rest, it is pulled down at 20. What is the frequency of the resulting oscillations? What are the minimum and maximum amounts of stretch of the spring? Force and then what is the frequency of the resulting oscillations? 2 pi. Okay. Wait, isn't the frequency just like the same?
Yeah, frequency is the same.
Oh, let's do pi. Let's do T. T equals 2 pi.
Anyway, yeah.
1.5 over 300 equals 1 times 2 pi 0.444 and F equals 1 over 0, which equals 2.25 hertz.
Oh,
Yeah, 2.25 hertz.
1 over 2 is the period 0.5, probably. Yeah, 0.5.
Minimum and maximum amounts of stretch of the spring during the oscillations of the block. This one you need the 1/2 300 times 0.02 equals wait, isn't it just 2 centimeters for B?
This is the thing. Let me draw the. So because it's a vertical now, right?
Oh, it have gravity.
Yeah, there's gravity.
So
Which means your which means your equilibrium point It's gonna be something gravity and something upward, right?
Yeah.
This is the mg, which means if you balance that, this one also mg, right?
Mm-hmm.
Which means there is gonna be a original something, original
energy?
x, original delta x to balance that mg, which is mg is basically negative kx in the beginning. Does that make sense?
Mm-hmm.
So they say
MG.
after it, the block comes to the rest. Is they resting in this kind of situation, right?
Yeah.
Then you kind of find that x then, right? Mg over k then, right? Or negative.
Mm-hmm.
Doesn't really matter.
MG
And at this
over
point,
K.
doesn't really matter. It must be mg over k. It's positive anyway. Right?
And so X is the like resting point.
Yeah.
Mm, okay. That means X is MG over K. 0.05. Okay, and then we can. So then it'd be 2 plus 0.05 and 2 minus 0.05.
Yeah.
Okay.
Which means like 5 plus 2, or I mean, if we talk about in centimeter, 5 plus 2 and 5 minus 2, right?
Yeah.
The highest position is probably 5 minus 2, and the lowest is 5 plus 2, right?
Yeah.
So just remember, when the vertical oscillation like that, there is gonna be a equilibrium point, right? And you gotta find that original length, which is not exactly the original length of the spring, right?
Mm-hmm.
Oh, this is something that we learned a little bit before. Well, not exactly, but we did see one of the like like this kind, right? It goes in here. There's a theta 30-degree thing, right?
Mm-hmm.
And if we say this is similar as this simple harmonic motion, yes, this is the one that we learned first. And this is the second one that we learn, also simple harmonic motion. And then that's the pendulum thing too. But it's not as well before what we have. It's E equals to 2 pi square root k over m, right? Well, actually m over k. And now if we study pendulum, if it looks like that, do they really? So eventually we can also find something in there. Also t equals to 2 pi, but this time not relate to mass anymore. The pendulum, well, we can try different mass, which doesn't really change the period. Does that make sense? Not as the spring constant, like not that spring, not like the block before. So this one does not, that the mass doesn't matter in here. But what matters is the longer the pendulum gets, the longer period. And on the other hand, we don't think about constant, the spring constant anymore. What we think is the, well, g acceleration, which is g here. They look similar, right?
Mm-hmm.
And why it's G is because if we change this, if it's the same length of the pendulum, if you do it in Mars, if you do it on the moon, it's different. Does that make sense?
Mm-hmm.
So which means what we use in here, we can use the pendulum and the clock, but we can't really use that on the moon because we have the same time. Is that making sense? So the G acceleration around that planet or star or moon kind of is going to be influencing my like period. You can imagine something doing this in here, something doing this on the moon, something doing this on the in Mars. Yeah, that's different. The period is different. If everything else is the same, the period is different. Yeah.
Mm-hmm.
So eventually, of course, the data shows that the same thing that we did, T over L over G, yeah, they are a constant, which is also 2 pi.
Mm-hmm.
Does that make sense? And why it's related to G, we kind of proved that in the question before, which is the same thing as this one. Does that make sense? See? Because this one, G acceleration have a component, if this is the theta. This one is mg sine theta, right? And this one is mg cos theta.
Mm-hmm.
So G is going to influencing my period. And this one is going to give me acceleration, so increasing the velocity. And this one is going to help me this is going to influence the circular motion, which means the centripetal force. Does that make sense? We know, remember last time we said T minus mg cos theta. Of course, the other one is the other theta, but it's the same thing. T minus, this is mv squared over r, right? Or L. Does that make any sense?
Mm-hmm.
And there is another one you can imagine, mv squared, kind of like delta ek kind of thing, depends on mg delta h. So because of this too, we can also help to deduce that. But also they don't deduce that anymore, so we can just better remember this. But of course, this drawing is necessary anyway, because we have circular motion, which is definitely going to be the test. Does that make sense?
Mm-hmm.
So this is also, do you know why it's called restoring force? I'm going to get back to here, right?
Yeah, because gravity is pulling it.
We divide this into mg sine theta, mg cos theta in here.
Mm-hmm.
Of course, because of this, we're going to have energy conservation, and we're going to have circular motion. The most difficult question about this. And we're going to have, well, geometry involved in there. And now T, which means, well, simple harmonic motion, and the time period in here. Is that making sense a little?
Mm-hmm.
So the most difficult question is, well, everything is involved. 12. Of course, we have T, then we can have frequency. So that's why we can have the clock. 12.
Small pendulum is 1 bit. A simple pendulum. A simple pendulum has a period of 1 second on Earth and a period beyond the moon when G is 1/6 of its body. Frequency 1/2 G over L. So we can just assume G is like, I mean L is like 1, right?
Yeah, because they always the same in there and in there.
So frequency, oh, we're looking for a period, so T equals 2 pi root 1 over 6. Wait, a simple pendulum has wait, do we need to find L?
Oh, you can find out. There's more than one method in this that I know.
I'll find L then.
Oh, you want to use the formula to get the L, right?
Yeah. Wait, 1 equals 2 pi L over 10. 2 pi 1 over 2 pi squared equals L over 10. So L equals 5 2 pi squared. So 5 over 2 pi, wait, 5 over 2 pi squared times 1 over 6. 5 over 12 pi squared. Where is this? 2 pi. That's so that means 2 pi times, okay, 2 pi 5 over 12 pi squared. So that's 1.29. 1.29 seconds.
1.29. You're using the new G is 1 over 6 times G, right?
Oh, whoops. Wait, oh. Oh, so this would be 10/6. Oh, shoot. Okay, wait. This would be 10/6. Okay. 5 over 2 2 pi squared over 10/6. Oh, so never mind. This is 2.45.
Yeah.
2.45.
Yeah, which means if we observe what we feel, is something that we see it on the Earth. And same one, we see it on the Moon. And this takes 1 second to do one period. And it goes from here to here and go all the way here. And from the Moon, we see here, and we see 1.445. So, which means we feel like why it takes more time, right?
Less gravity.
Yeah, less gravity. So what the time is actually the same thing, right? If 2 seconds means 2 seconds on the Moon, also 2 seconds on the Earth, it's the same thing in the universe, because well, the universe is inside time. Or this is okay. Or you can do is just because this is 1/6, right? Which means it's a ratio, right? When ratio happens, we also like to do like a division. It means, for example, this is T1 and 2 pi square root L over G, and T2 is 2 pi L over 1/6G, right? I can divide that, right? I divide T2 over T1, which is gonna be everything simplified. Then I flip that with 6G, which is square root of 6. Wait, it is square root of 6, right? So T1, T2, also because this is 1, also means T1 times square root of 6, which means 1 times square root of 6, which is same thing as your 2.45 thing. Does that make sense? Using the ratio, it's also okay. Does that make sense? But when they have ratio, we can use that. So the homework would be just chapter 9. Real questions.
No.
Of course, everything that we do in class also included in the homework.
Yeah.
Do you have other questions?
No.
Okay, then have a good day.
Okay. Yeah.